Next, we have to study the magnetic field intensity due to a solenoid. That's also an application of Ampere's circuital law. Magnetic field intensity due to a solenoid. We all know that solenoid means a long wire wound in the form of a helix closely wound on a non-conducting frame forms a solenoid. Solenoid means a long wire wound in the form of a helix closely wound on the non-conducting frame forms a solenoid. Okay, that I have shown in figure. So it can be considered as number of circular coils tightly bound to form a single unit. The magnetic field produced by solenoid is taken as the vector sum of field due to all these circular coils. Okay. So figure I have shown. So to find the magnetic field due to a solenoid, we can use Ampere's circuital law. For that, we let us consider a solenoid of length capital letter L and small letter n number of turns per unit length carrying a current capital letter I. So to find the magnetic field intensity capital letter B, imagine a closed path of length small letter L and breadth B. So applying Ampere's circuital theorem, closed integral B dot dl is equal to mu 0 sigma I. Then substituting the terms for the closed loop, closed integral B dot dl is equal to from A, B, C, D we have noticed in figure. Here it is S, P, Q, R. So the integration from PQ B dot dl plus QR B dot dl plus RS B dot dl plus SP B dot dl, all are vectors. So the equation becomes final equation B dl cos theta here is 0 degree. So closed integral B dot dl cos 0 degree, and after calculation we get B outside and closed integral B dot dl is equal to A, and we get final equation as mu 0 I0 is equal to mu 0 n A I, or B is equal to mu 0 n0 I, the final equation. That's just calculation only. Or B is equal to mu 0 ni, final equation. Okay, that's about a straight solenoid actually. So solenoid we can consider another form also. That's why we can say that's a toroid. What's a toroid? Toroid means it's an endless solenoid. Endless solenoid is called a toroid. That is when a long solenoid is bent to a circle by joining its two ends, we get a toroid. By joining its two ends, we get a toroid. It's an endless solenoid. So to find the magnetic field produced due to current flowing through a solenoid or a toroid, we can here also apply the Ampere's circuital theorem. Here also consider a toroid with a capital N number of turns, mean radius small letter r, carrying a current capital letter I. Then applying Ampere's circuital law, B dot dl, closed integral B dot dl is equal to mu 0 epsilon I or sigma I. And here the angle theta is equal to 0 degree. So closed integral B dot dl is equal to B dl cos theta. That's equal to mu 0 capital Ni. And after further calculation, we will get capital letter B is equal to mu 0 Ni, where small letter n is equal to capital N by 2 pi r, that is number of turns per unit length. So we'll get the final equation as B is equal to mu 0 Ni itself for the case of toroid. Okay.